Hello everyone, this is Sean Mullery from Electronic Engineering and IT Sligo, and in this lesson what we're going to look at is using both a counter and a timer together in order to achieve something. So what I'm going to do in this particular case is I'm going to get timer 0, and I'm going to use it as a counter, and I'm going to count a particular pulse coming in on RA4. What I'm then going to do is I'm going to time how long I should count that for, and I'm going to use the timer 1 for that. So I'm going to time it so that I can use it for 1 millisecond. So the idea here is that my timer 1 will time 1 millisecond, and my timer 0 will count pulses coming in on the port pin for that 1 millisecond. So I'll then use the interrupt for the timer 1 timer for when it overflows to decide what to do at that point. So what I'm going to do at that point is I'm going to put the value from the counter into a variable which I'm going to call frequency. And this is one way in which we could use to try and determine what the frequency of a pulse that's coming into our microcontroller might be. So in order to do this, I'm going to have to do quite a bit of initialization. As always, I'll do my ANSEL and just set it to 0. I will set up port A, and I'm only interested in pin RA4, so I'm just going to set that to 1, 0, which will set up RA4 as input. Okay. Now, a number of things I need to do now. I need to deal with timer 0 as a counter. Sorry, I just want to bring that back to where it should be. Now, so I want to put timer 0, so that's going to be T0CS. Hopefully you remember many of these things from the previous one. If not, go and look up the document and you'll hopefully recall them. So I'm setting that up as a counter. I'm not actually specifying which particular edge I'm concerned about in this case because of the fact that the pulse I'm going to use is a 50% duty cycle. In other words, 50% is the time high, 50% is the time low. It shouldn't make an enormous difference which edge I would pick. In other circumstances it may do. So I'm going to keep it out of this for the moment in order to keep it a little bit simpler. So timer 1 then, and what I want to do, actually I'm going to leave this one to last because that's turning the timer on, and I firstly want to enable the timer interrupt. That's the timer 1 interrupt enable. I'm going to set that. So I'll just say I should of course also put a little comment here for this is to set up timer 0 as a counter. Now, this idea of a timer and a counter, it should be pointed out that a timer is in fact always a counter. In the case where we're using it as a timer, it's simply counting the number of times that the instruction cycle clock, how many instructions actually go by, or how many instruction cycles go by. So it's still counting there. When we use it as a counter, we're counting something from an external source. So in both cases, a counter, a little bit like the watch on your arm is a counter. It's counting the number of seconds that go by. Okay. So in this particular case, all we're really doing is we're changing it from counting the instruction cycles to counting an external pulse or an external event that could come in. Now timer 1 on, I'm going to set that to 1. So this is to set it running. Okay. Now the thing is, I haven't actually put a start value in timer 1 either, which I normally should do if I wanted to count a certain amount of times. But I'm actually not too concerned about it in the first case. I'm going to let it count whatever it does, cause its interrupt, and then once I'm in the interrupt, I'm going to set that up properly. I could set it up here if I needed to, but I'm not going to do it for simplicity's sake in this case, no other reason. I'm going to set the global enable to 1. to set up the global enable interrupt enable. Okay. And the peripheral interrupt enable. Now, and then I've set the timer running. Now, as I said, if that starts at 0, it's actually going to have to go its full 16 bits, which would be about 65 milliseconds before it'll actually occur for the first time that the actual interrupt will occur. I'm not too concerned about that, but I could put a starting value here should I wish to. As I said, in order to keep it simple and the video as short as possible, I'm not going to do it here. So the next thing is I want to set up my my interrupt. So I'm in my interrupt here, you can just see. And one thing I've left in here just to remind myself in case I forgot is that I've put in an external unsigned int called frequency, or FREQ. I've just shortened it to FREQ. Now, because I've called it an unsigned int in this case, rather than an unsigned char or character, it means it's going to be 16 bits in this case, so we're able to hold numbers bigger than 255. So the interrupt that I'm looking for is timer1 interrupt flag, and I'm waiting to see is that equal to 1. If it is, I'm going to put the TMR1 on. I'm going to switch that to off. Now the reason for that is that I wanted to stop running at that point because I'm going to do a number of things inside the interrupt and I don't want it to start again until after that. Okay. Again, we could actually let it run on, but the thing is we're actually going to reintroduce a value into it and set it going again, and therefore it's not really a good idea to actually to do that until the end of the interrupt. Now we'll try and keep the interrupt as short as possible, so we'll try and put as little in here as we can, but beyond that we don't want the thing to be running and counting up instruction cycles in the middle. So what I'll also do is, and you must remember to do this in each of the cases, is we need to set the timer1 interrupt flag to 0, and I shouldn't say set to 0, I should say clear to 0. Or reset to 0. So we're putting that to 0 in order to cancel out the flag that has occurred, so that when it occurs next time, it's not that when we leave the interrupt we're immediately going to be called back because we forgot to clear it. So I'm then going to put a value into frequency. I'm going to put the current value of TMR, and be very careful here, I'm putting in the value of timer 0. That's because it's the one that's doing the counting of the pulse on RA4, not timer 1, remember. And then what I'm going to do is I'm going to reset up timer 1, TMR1. Now if you're looking up the document, you may see this as TMR1L and TMR1H for high and low byte. That's particularly useful if you're putting it in an assembly or whatever, but I'm just going to use it all as one variable here, and I'm going to put in the following value. I'm going to put FFFF because it's the 16-bit variable. That's the largest number it could hold, and I'm going to subtract from that the number that I actually wanted to count by. I wanted to count 1000. Why 1000? Well, that's going to be 1 millisecond. Now, when I say it's 1 millisecond, that's assuming that we have a 4 megahertz clock. If we have something other than that, such as a 12 megahertz clock, I would have to change my timings and the amount of time that the timer runs for. So it's not that I can give a straight answer to you here. It really depends on what your clock frequency is as to what you put in there. I'm just assuming that it's a 4 megahertz clock, and I'm assuming that in the simulator input that I'm putting in as well, so that the two of them combine and line up with each other. Now, finally, what I want to do is I want to put the TM or 0, I want to put that back to 0, so it's ready to start counting again from 0, and I want to put TM or 1 ON. I want to start up the timer 1 once more. by putting that in there as a 1. Okay, so there are all the things to do there. I really don't do a huge amount in main. All I'm really going to do is, and I've probably already left it in there, I have indeed, unsigned int frequency, and I've set that to 0 there, just to, or cleared it to 0 if you prefer, but I'm initializing it, I suppose is the proper word to use, initializing it to 0. So when this runs, we'll have this while 1, it'll go on and on, but the real information actually happens, or the real data processing happens in the interrupt. And what we're going to do is we're going to try and figure out how many times either a positive edge or a negative edge, in other words, how many periods of the incoming waveform have occurred during the 1 millisecond. Okay. So to do this, I would have to put a stimulus in, and what I've done with the stimulus here is it's currently low for 100 cycles and high for 100 cycles. I'm actually going to go for a different figure than that. I'm going to go for 50 in each case. Now that puts the entire, 50 low and 50 high, that's 100 in all, 100 cycles for the full period of that waveform. Now if it's 100 cycles, that's effectively 100 microseconds that it will take for a full period of that waveform, and therefore we would assume that there would be 10 of those in 1 millisecond. So hopefully our counter after each go will show us a value of 10. So we'll give that a run there. Okay. Now I just want to, it's a good idea anytime you make a change to hit that and then to hit it again to make sure that the stimulus is applied successfully. In my watch windows, make sure you've got a watch that's watching the frequency. And you do that by right mouse clicking and adding a new watch. I'm not going to do that because I've already got it there. And I'm going to pause there, and I'm glad to see that in frequency I have the value 10. I'm going to run it again for a moment. Stop it. I now have the value 11, so let's be careful of that just to see does that happen more than once. It's gone back to 10. And there's 10 again. And there's an 11. So what we can see here is that the answer it's either given is 10 or 11. Okay, we see an 11 again. And an 11 again, and we'll try it one more time. And we're back to number 10. Now the reason for this is that it's clearly a situation has occurred where the two things are not perfectly in sync with each other. In other words, the 1 millisecond and the running of the clock at that. And therefore, what could theoretically happen is because it's counting edges rather than counting the full length of the period, there is a chance that if it's slightly out of skew, it may actually manage to get 11 edges in the time rather than only 10 edges. So that's one to be wary of, because even if it gets if it only gets 10 edges, it means that there's another edge coming along very, very shortly. So that's somewhat to be expected, and that's a kind of an error you may have in there. Again, all you have to be out is by a few microseconds, and you could get that extra edge in there. So generally speaking, it's not a bad idea to have your timings a good bit longer than the actual signal that you're trying to check. So in this case, it might be better if we actually check for 10 milliseconds or for 100 milliseconds as opposed to just checking for 1 millisecond. What we'd find then is if we check for 10 milliseconds, for example, we'd probably find that the number 100 and the number 101 is coming out regularly. So instead of, in this case, where it's coming out as 11, which is wrong by 10%, we'd only be coming out wrong by 1%. And if we did it by a bit longer again, we'd only be coming out by maybe 0.1%. So that's a useful thing to be able to do. Now, even at that, if I have a signal that's low for 50 and high for 50, in other words, a full period of 100 microseconds, the actual frequency of that is not 10. Okay, in hertz. So what I'm going to do is I'm going to give you an exercise to try and figure that out. How would you change it to make sure that what this frequency variable actually held after each go was the actual frequency of the signal and not simply just giving me a number? Okay, so there'll be a few things I'll be asking you to do. I'll be asking you to try it for different frequencies and also to actually see if you can report the actual frequency. The reason I want to do that is because later on we might want to do this as an exercise to report the actual frequency on something like a liquid crystal display, or to send it on the serial port to display it that way, so that we could then send the information to another device to say what the frequency of some signal was. Okay.